No matter how we structure a mathematical expression or which letters we use to label the variables, our calculations and our general conclusions remain the same. You might be surprised to find out that E equals mc squared never appeared in Einstein's original 1905 paper. He even used the letter L instead of E to label energy. He arranged the expression a little differently because he wanted to highlight the change in mass instead of the energy that's emitted. The original equation Albert Einstein used was m equals L over c squared. He wrote this because if a body gives off a certain amount of energy, L, in the form of radiation, its mass diminishes by L over c squared, where c is the speed of light. We have to understand this equation in the specific context of emitting and absorbing radiation between objects. Radiation conveys inertia between objects, which changes their mass. According to this theory, mass actually measures the total energy of an object. M equals L over c squared might look like a complicated expression, but we can interpret it more efficiently by viewing parts as a single entity. The best way to think about it is as a linear function with one input, energy emitted, and one output, mass lost. You're probably familiar with the equation of a straight line, which is y equals mx plus b. We can ignore the constant b and simplify the equation of a straight line to y equals mx. You'll see that there's one term on either side of the equation, y equals mx. On the left side of the equation, there's a single term, y. And for our purposes, y is like m. On the right side of the equation, there's a single term, mx. This term is made up of a variable, x, and a coefficient, m. Mx is similar to L over c squared because L over c squared is made up of a variable, L, and a coefficient, 1 over c squared. It's helpful to think of the coefficient, m, or 1 over c squared, as the slope of the line when you plot the equation on a graph. The slope remains a constant factor at every point along the line. Now, if we were to replace L with 0 in this equation, the result would be mass equals 0, and that's what we would expect in real life. On the other hand, replacing L with a positive value in the equation to represent the amount of energy that's emitted by an object, that would give us a positive amount of mass that is lost during radiation, and it would tell us the exact amount of mass lost. For now, we will stick with Einstein's original equation, so pay no attention to E equals mc squared. Regarding grams and joules, which are the units we're using, if the energy changes by L, joules, then the mass of an object changes in the same sense by L over 9 times 10 to the power of 13 grams. Now, this equation lets us calculate the exact exchange of mass and energy during radiation, and it should hold true regardless of any other properties of the objects. Now, let's look at a concrete example of this theory by using objects that I have right here.